Hello there, welcome to a presentation on Introduction to Ordinary Differential Equations. My name is Charles Wasfan Msipa. Now the first question to ask in this case is, what is a differential equation? A differential equation in simple is an equation in which appears derivatives of an unknown function. Like for example, in this expression, we see we've got derivatives of y. In this case, y is an unknown function. So, and that one of the most important things to know when we're in the presence of a differential equation is what we call the order of a differential equation. So what is an order of a differential equation? The order of a differential equation is simple, the order of the highest derivative, the highest order of a derivative which appears in the equation. For example, in this case, let's say all the an's were equals to 0 except for probably, let's say, a2, a1, and a0. Then we'd have an equation of this form: a2 d2y dx plus a1 dy dx plus a0 y equals to f of x. In this case here, we would say we've got a second order differential equations. So talking about the equations, the order of an equation, we have here this equation which is dy dx equals to this expression, and this we normally call the initial condition which is given to the equation. We're going to see that later. So this is the first order equation, and here is the second order equation, and here the unknown function is function u of t. That is what we are. So a differential equation is simple, an equation in which appear derivatives of an unknown function, and solving that equation, which simply means determining the unknown function. Proceeding, for what purpose are differential equations? In science and engineering, given a differential equation like this, depending on the context, the differential equation would model a system as an input-output system, in the sense that the right-hand side, the left-hand side of the system here, where we've got f of x, that will be the input, and the unknown function y will be the output. So, solving a differential equation of this nature, it will basically determining the function which sort of models the output of the system. And also important, in an equation like this one, we could have two cases. One, if f of x in now the right hand side of the equation is equal to 0, we would say that we've got a homogeneous equation. In other words, the system, the input to the system will be 0. On the other hand, if f of x is not equal to 0, we would say we're in the presence of a non-homogeneous differential equation. So solving a differential equation, what is the solution to a differential equation? And solving differential equation simply means determining the solution, determining the unknown function in the differential equation. And then a solution to a differential equation will simply mean a function which satisfies the differential equation. For example, let's say with an equation 2x plus 1 equals to 5. Now, somebody could just throw a number and say, find out is x equals to 3 a solution to this equation. What we do is we'll simply check whether 3 satisfies the equation. By satisfying, we mean that when you substitute this number 3 in the equation must balance. In this case, check, we'll say here the left hand side here is given as 2x plus 1 given x equals to 3, which will give us 2 times 3 plus 1, which will give us 7, which you can see this is the left hand side, but the right hand side is equals to 5, and definitely here the right hand side we can see that it's not equal to the left hand side. Then in that case we would say 6 is not the solution to the differential equation. You can check if you want. I mean, it's easy to see that the solution to this equation is x equals to 2. So here I'm just trying to explain what does it mean to satisfy the equation. So now we've got this equation here, and we are asked to verify whether these functions are a solution to that equation. What would you do? We would simply, in this case, we see in the equation you've got a second derivative and the first derivative and the function itself. So what would you do? We would say, let's say we put our right hand side here as 20 cos 2t. Then for the left hand side, we've got this expression which says du dt squared plus 3 du dt plus 2u. That's our left hand side. In this case, we're given, let's take for example this first function here. We're given that u is equals to minus cos 2t plus 3 sine 2t. So what would you do now here? Would simply need to differentiate this function twice to substitute here and see whether we get the solution, we get the equation balancing. So differentiating for the first time du dt, this will give us 2 cos 2t. Differentiating for the first time, this will give us a plus 2 sine 2t plus 6 cos 2t. That will be our first derivative there. And then the second derivative is going to be 4 cos 2t minus 12 sine 2t. Now I've got to substitute all this in this expression and see what we get. So I will do it this way. I will first of all write this second derivative here as 4 cos 2t minus 12 sine 2t, and then there we need to multiply this the first derivative by 3, which will give us 18 cos 2t, multiplying this 3 and that's 6, plus 6 sine 2t plus minus 2 cos 2t plus 6 sine 2t. And all this we're adding. I wrote my terms here in such a way that they are organized that I can easily add. So we can see here that this is 12 minus 12, that will be 0 there. And then when you come here, you got 4 plus 18, which will give you 22, minus 2, which will give you 20 cos 2t, which in this case, this is identically equal to the right hand side. So what we can now conclude, we can now conclude that therefore ut equals to minus cosine 2t plus 3 cosine 2 is a solution. Of course, is a solution to the given differential equation. So I'll leave this other solution for you to. I'll then leave this other expression for you to verify whether it's a solution or not. But exactly this is the process. You've got to do what the differential equation instructs you to do, find the derivatives, substitute accordingly on the left hand side, and see whether you get the equation balancing. Then you can conclude whether it's a solution or not a solution. So I hope by that you understand now what we mean by a solution to a differential equation. We simply mean a function which satisfies the differential equation. Now, in this presentation, we are going to look at the method of solving differential equation called direct integration, and we're also going to look at the method of separation. Later, we're going to look at these other three approaches of solving differential equations. So we start here first by direct integration. Now, when we're talking differential equation, actually the first time you were introduced to a differential equation is when you were doing what we used to call we call integration. Like for example, given a problem like cos 2t dt to integrate, this problem implicitly suggests that there is some function y such that dy dt is equal to cosine 2t. So what we're doing here, doing integration, you are actually solving this type of first order differential equation. So you will see sometimes in some books when they say solve a given differential equation, they will say integrate the following differential equation, meaning exactly this. So what we do here to find this, to find this this y, what you do basically would integrate on both sides here, which ends up giving us this kind of expression. Then we'll say here y, taking from there, integrating from both sides, because what we are saying here that whenever we are given a derivative or function, in order to recover the function, we've got to do the inverse process of integration. So we say here integrating both sides there, we end up with y equal to the integral of cosine 2t, which is the usual integration problem which we are used to. So then integrating that, you would simply modify the expression under the integral accordingly in order to have the kind of a derivative which you want under integral sign. Because remember, usually what appears under integral sign must be a derivative or something which at least can be transformed into a derivative. So what I'm trying to do here, I'm trying to transform this to a derivative for which I can give a direct answer. So after this, I would take out the constant half and leave here 2 cos 2t dt. I hope you see that my transformation here, what does it do? It gives me a cosine 2t multiplied by a derivative of argument, because we know that a derivative of a function is always the derivative of the immediate function multiplied by the derivative of the argument. So here we would know that cosine is an immediate derivative of a function sine, and then this 2 is the derivative of the argument. I'll write here derivative of the argument of the function which is being differentiated. So once I've seen that this is I've modified this to a derivative, then I can integrate by meaning that this integral sign simple asks for the function which has been differentiated to get this kind of a derivative. Then our answer there will be simply sine 2t multiplied by this half, then write as sine 2t over 2 plus a constant. So this is a kind of a first example of doing solving an equation using direct integration. And then once you've got a solution like this, you can double check whether it satisfies the equation. I'm sure you're going to see that it satisfies the equation. And this c here is an undetermined coefficient like we did in integral. Then this solution, we're going to call it a general solution. That will be a general solution. So if we were given, like for example, in this example that we're given an initial condition like this, if we then evaluate this, the general solution using the initial condition, we're going to get the opposite of general, which will be a particular solution. So in this initial example we are given here, we're actually required to find a particular solution given this differential equation. So solving that, this is what we do. We'll simply integrate on both sides here, then say y is equal to the integral of the sum function, which is 8x plus cosine 2x dx. And then integrating this, we know that this is going to give us 4x squared using power rule. We say x squared divided by 2, then we get 4x plus, we've already seen what's the integral of this, which is have there. Then we just have here cos 2x over 2 plus c. Then this is our general solution, and we can write here yg just to indicate that this is our general solution. Now, taking into account this condition here, we say y at 0 equals to minus 3. This implies that if you evaluate this function at 4 times 0 squared plus cosine 2 times 0 all over 2 plus c would get minus 3. So we can see that, we've generated an equation there which has got c as an unknown. But this is be 0 and this will be 1 over 2, which is half. Then we have half plus c equals to minus 3. And then this gives us that c is equal to minus 6 over 2, which is this minus 3, minus half, subtracting half here on both sides here on the equation. We get this, then you get this as minus 7 over 2. So once we've got this c now, we can now move from here and write a particular solution where c has got this value. So giving our particular solution, we write y particular, which will be 4x squared plus cosine 2x over 2 minus 7 over 2. Then this is our particular solution. I hope that is clear. So what we can do now, we can get to your text and do further problems of this nature, especially determining a particular solution. Otherwise, the rest is the usual integral which we are used to, in as far as we are talking about the method of direct integration. Then coming to the method of separation of variables. First of all, it is important to, when you are given an equation, it is important to realize whether there is a possibility of using the approach which is supposed to be used when the differential equation is of separable variables. So the question simple is, when do we say a differential equation is of separable variables? The answer is clear. A first order differential equation for which you can factorize the right hand side in such a way that one factor is a function of x and the other factor is a function of y is an equation which you can describe as an equation of separable variables. So it's easy to explain this using an example. So for example, we've got an equation here. So first of all, because before we declare that it is of separable variable, we should see whether we can factorize the equation this way, or at least if we can do some algebraic manipulation in such a way that at the end we've got on one side of the equation expressions in terms of y and on the other expressions in terms of x. This is what we're going to do here. So let's say solution to this problem. We've got 2 here, 2y dy dx. This is given equals to e to the power of x minus y squared. So the approach I'm going to use here, I'm going to manipulate this equation in such a way that on one side of the equation I have expressions of y, and on the other I have expressions of x. So the first step I'm going to do here, I'm going to multiply the whole equation by e to the power y squared, which here, first of all, before when I do that, what's going to happen, I'm going to have this as e to the power x minus y squared plus y squared using rules of exponents equals 2 dy dx 2 y e to the power y squared. And then this will give us 0. Then we get here e to the power of x. And now our problem is only this dx, which is this side. So we multiply again here both sides by dx, and then we get 2y e to the power y squared dy equals to e to the power of x dx. And then once we've got this, we've got to revert back to or evoke the method of direct integration. In this case here, we would simply integrate both sides. So this is equivalent to integral 2y e y squared dy equals to the integral of e x dx. And please take this into account. When we're integrating definite integral, we always added a constant. But in this case, I would advise you to add constant only on the side of the independent variable. How would you get that this is the side of the, you see this is dy dx, y with respect to x, simply means that y is the dependent variable and x is the independent variable. So in this case, we're going to add the c only on the side of the independent variable. So here the integral is simply ex plus c. I hope you still recall your integrals. Then when you come here, if you are struggling with this, you should remember that an exponential function always appears in its own derivative. So the best thing to do is to pick the exponential part of this, because you are trying to make sense of which function was differentiated here in order to get this kind of derivative, which is e to the power y squared multiplied by 2y. You can use also the methods of substitution, whichever, but if you want to use some kind of a trick, you can just simply take this and check what happens when you differentiate that. So if you've got e to the power y squared, you differentiate this, you know that the derivative will come with e to the power y squared multiplied by the derivative of the argument. Now, the argument is y squared. You use power rule there, you get 2y. So, which simply means this is the derivative of that. What is under the integral sign here is the derivative of this. So, your answer here simply should look as e to the power y squared. And then what we have here, you can see that our y, the solution y, is given in an implicit way. So whenever it is possible and whenever it is manageable, you must always try to leave your y as subject of the formula. So what we're going to do here, we're going to apply ln on both sides of this equation. Then we have ln e y squared equals to ln of e to the power of x plus c. And on the right hand side here, you can see this is going to give us y squared, because ln is the inverse of e, and then we've got ln e x plus c, and then this we can say therefore y is the square root of ln e x plus, so in this expression here, we consider that e to the power x plus that is greater than 0, because ln won't take arguments which are negative there. That is important to take into account. So that is our first example of solving equation using the method of separable variables. The next question is an example also. We've got two problems here. I'm going to leave one of them for you to try on your own. In this case here, let's do number 2, part 2 here. Let's have here solution. So the equation is dy dx equals to x squared minus 1 all over xy plus y with given condition there. So if, let's say this problem will be mixed up with the other types of problems. So if we suspected that it is of separable variables, we simply need to factorize this and have an f of x multiplied by a g of y. Please take into account that this covers also division, because multiplication and division, multiplying is same thing as dividing by the reciprocal. So even if we had something like this, f of x over g of y, essentially we've got something like this, because here is simple text that you take g of y here, we take 1 over g of y multiplied by f of x, which is again reducible to something like, we take this as h of y, we can take this as h of y multiplied by f of x. So you mustn't be confused by how this expression looks like, whether it looks like a quotient or just simply product is one and the same thing. So what we're going to do here now, we're trying to do that. We check here, we see that there's a common factor y in the denominator here. So then we write this as x squared minus 1 over y brackets x plus 1. And then this we can write as 1 over y multiplied by x plus 1 over multiplied by x plus 1 times x minus 1 over x plus 1. Simplifying this, you can see that you've got two functions here, one in terms of y and that. So it's an equation of separable variables. Simplifying this, it gives us x minus 1 over y. And multiplying both sides by, in this case here, or multiply both sides by y dx, what we immediately going to get here is y dy equals to x minus 1 dx. And then from there, we can do direct integration on both sides of the equation, and then integrating, we get here y squared all over 2 equals to x squared over 2 minus x plus c. And then simplifying this, we can multiply both sides by 2. We have y squared equals to x squared minus 2x plus c. I'm going to write c again here, because if I've got c, a real number, I was trying to throw the real numbers. If multiplied by 2, I'll simply get a constant again, which is a real number. So we'll leave it like that. Then finally, we've got y equals to the square root of x squared minus 2x plus c. And then now, using this condition here, we're told that y at 0 is equal to the square root of 2. So when we say y at 0 is equal to the square root of 2, we simply mean that the point 0 comma square root of 2 satisfies the equation, or otherwise it's on the graph of the function. So what we're going to do here, we're going to subtract x coordinate everywhere there's x by 0, and evaluate y here at 0 and get that. So we're going to say y at 0 equals to square root of 0 squared minus 2 times 0 plus c, which will give us, we say this is given a square root of 2, so we're going to have this as square root of 2 equals to the square root of c. And then we can conclude that squaring both sides there, we've got that c is equals to 2. Then we can write our solution here. This is our general solution, or we can look at it in that form. Then we can write our particular solution now as yp, we can write this yp at x equals to the square root of x squared minus 2x plus 2, and then that is our particular solution. So I hope the two examples we've looked at here, first the direct integration, we looked at it because you can see in the final analysis, in the process of using the approach for separable variables, it actually involves doing direct integration at some stage. So that's why we looked at these two approaches together here. Otherwise, at this point, I would like to say thank you for listening. My name is Charles MC.